Thank you. Thank you for your introduction. Thank you for your invitation. It's my great pleasure to give a talk on ideas. Today I will talk about uniform Turan density. In fact, it's a problem about embedding a uniformly dense hypergraph. This is a joint work with Holly from Guanghui University and Lin Hao, Wenlin Zhou are from Shandong University, and now they are both in Europe. In the first part, I will give some background or some motivation. So as we know, extremal graph theory is a rich branch of combinatorics. In fact, it deals with how general properties of a graph influences the local structure of the graph. In fact, we want to embed some subgraphs in different kind of graphs, or in graphs under certain conditions, the number of edges or minimum degree conditions. For example, the mental theorem states that if a graph on n vertices and the number of edges is above n squared over 4, then this graph contains a triangle. Here, a triangle is a local structure, and number of edges or density is the general properties. We have the same style in other fields, such as the number theory or additive combinatorics. The famous Ross theorem implies that if we choose a subset with positive density, then it contains a three-term arithmetic progression. Here, the three-term arithmetic progression is x plus y, x plus 2y. Right? And interestingly, these two questions are strongly related. Because it's very difficult to find the optimal density guaranteeing the three-term arithmetic. In fact, it's equivalent to the following problem. To determine the maximum number of edges in any vertex graph where every edge is contained in a unique triangle. So in extremal combinatorics, we are often interested in the host set, such as the graphs, hypergraphs, or sets, vectors, even integers or primes. And the local structure we are interested in cycles, cliques, or some spanning subgraph, the vector or Hamiltonian cycle. In extremal set theory, there is some interesting structure, the intersecting family or some flowers. In normal theory or even in the integers, we are often interested in the arithmetic progression or some solutions for some linear or nonlinear equations. And there are many beautiful results, such as the Turan, the mental theorem is about the Q3, and Turan's theorem is about the clique. And the Hajnal summary theorem is for the clique factors. And for the intersecting family, we have the famous Erdos-Hajnal theorem. And about the number theory, we have the summary theorem about the key arithmetic progression. And the Green-Tau theorem states that there are key arithmetic progression even in the primes. Now let's go back to the extremal graph theory. Let's consider the Turan number. As we know, the Turan number is the maximum number of edges that a graph on n vertices there's no copy of f can have. And previously we have the famous mental theorem, Turan theorem. As for arbitrary arbitrary graph F, there is the Erdos-Hajnal theorem. It means that the Turan number is related to the chromatic number of F, where Kf is the chromatic number of F. In fact, we can define the Turan density. So even we consider the key uniform hypergraph. So given a key graph F, the Turan density is the maximum edge density that a graph or hypergraph can have, which is F3. As for graphs, the Erdos-Hajnal theorem means that the Turan density for graphs, for any graph F, is the chromatic number minus 2 divided by the chromatic number minus 1. So we have many possible Turan densities, such as 0, 1/2, 2/3, and so on. And for the Turan density of a hypergraph, I mean the key is at least 3. It's very difficult to determine the Turan density. So Erdos' theorem states that if the Turan density is 0, if and only if F is a key part of the key graph. We use key for 3 means click on 4 vertices in 3 uniform hypergraph, and the key for 3 minus means click on 4 vertices minus an edge. Even for the click on 4 vertices, we didn't determine the Turan density, and we know the lower bound is 5/9, and the upper bound is 0.5615 due to the famous flag algebra, and the lower bound is the construction due to Turan. So we divided the vertex into 3 parts. V1, V2, and V3. So there are 2 kinds of edges. One is one kind of edge meet each VI exactly 1 vertex, and another kind of is something like this. We use 2 vertices in V1, 1 vertex in V2, 2 vertex in V2, 1 vertex in V3, and so on. So it's easy to check that the Turan density is about 5/9, and there is no any key for 3. Or even about the key for 3 minus, we don't know the exactly value. It's between the 2/7 and 0.2871. And luckily, we know the Turan density about the final plane. It's 3/3. So last year, Kensev later and Pokovsky determined the tight cycle. CL. CL is tight like in 3 graphs, where error is large and it is not a multiple of 3. It's a very nice and interesting result. Because the construction is an iterative construction. So now we talk about the uniform Turan density of hypergraphs. So in 1982, Erdos-Hajnal proposed to study the Turan density and uniformly dense hypergraph. So because they find that the extremal hypergraph is the edge distribution is highly uneven. So they want to consider the hypergraph with additional requirement that the edge distribution is uniformly or randomly. They give the d mu dense hypergraph. So given d and mu, hypergraph H is called d mu dense if for any u, for any subset u, the edge density inside u is around d. And then they define the uniform Turan density is the supreme of d for every mu, and there exists F3 d mu dense 3 graphs H.
So n is the number of vertices of H, right?
Sorry?
N in the inequality, the n is the number of vertices of H.
So H, the number of vertices is large.
And on the first inequality, there's an n.
You mean the uniform Turan density?
No, mu n.
Yes, yes.
N is the number of vertices.
Yes.
Yeah, okay.
Yes. For any u, because when mu is large, then it holds clearly. And clearly we know this bound. So the classical Turan density is cannot be lower than the uniform Turan density. In 2018, Raya Roda and Matthias Schacht give a characterization for F with the uniform Turan density 0. For graph F, the uniform Turan density for F is 0. If and only if we can give an order of the vertices F V1, V2, and Vf, and give a coloring red, blue, green to the shadow of F. Okay. So where the shadow is the pair of vertices covered by an edge. Red. And for any edge E, for example, Vi, G, with I, this order, the color pattern is exactly Phi, Vi, Vg is red. Red, blue, and green. So this is a nice characterization for the hypergraph with Turan density 0. So it's clear to check that the three-partite 3 graph, the uniform Turan density is 0, because we can easily to give an order. V1, we choose something like this and color this one or red, blue, green. And also it's easy to check the linear graph. The linear hypergraph, the Turan density of linear graph is 0. And besides these two kind of graphs, there are the tight cycle on, for example, the tight cycle on 5 vertices minus 1 edge. It is not a tripartite 3 graph, and it's not a linear graph, and the uniform Turan density is 0. And they have a corollary. If the uniform Turan density is positive, then it should be larger or equal to 1 over 27. And the last year, Gab, Krell, Lamson give a construct a kind of graph with uniform Turan density 1 over 27. So it's, this results prove the conjecture of the Matthias. And both Cooper and Krell, they determined the uniform Turan density of a tight cycle. So when here the t is at least 5, because when t is equal to 4, it is exactly the key for 3, the clicks on 4 vertices. So when t is a multiple of 3, then the uniform Turan density is 0, and otherwise the uniform Turan density is 4 over 27. As for the clicks on 4 vertices, the Roller's construction implies that the lower bound should be 1/2. And Balog, Clement, Lidisi, they use the flag algebra to get upper bound 0.529. And for the key for 3 minus, it is a click on 4 vertices minus edge. The lower bound should be 1/4. So because when we can randomly we have a random tournament. I mean we oriented each edge of a complete graph uniform and randomly. It's easy to check when there is a cyclic triangle. Then there is we put an edge in a graph with on the same n vertices. It's easy to check that the density is about 1/4, and there's no key for 3 minus. And this conjecture was proved by 2 groups. One group used the flag algebra, and another group used the hypergraph regularity method. This year, Chen and Shuk, they gave another kind of hypergraphs with uniform Turan density 1/4. In fact, it's key for 3 minus with additional vertex x, and we put 2 edges into this graph such that the link of x are 2 matchings. So x, the link graph, for x the link graph are A, B, and DC. So they prove that this graph, the uniform Turan density is still 1/4. Okay, well, our main results is we give a sufficient condition for the uniform Turan density is at most 1/4. So it's a little complicated. So what's the sufficient condition? So we can give the f an ordering V1, V2, Vf, and there is a 3 coloring of the shadow. So we map the shadow into a color set: red, blue, green, violet, cyan, black. And for each edge, it's exactly one of the 3 keys. Okay. So if IJK is belong to F, then the color pattern could be blue, white, red. And there is a integer I star. If IJK belong to I star, then the color pattern could be green, cyan, blue. And if I star is between J and K, the color pattern is green, black, and red. So this sufficient condition is a little complicated, but it's easy to check that key 3, 4 minus satisfies this property, because we give ordering 1, 2, 3, 4, and I star, we choose Y star is 3. We give the shadow of the key for 3 minus with this coloring. 1, 2 is green, 1, 3 blue, 1, 4 red, something like this. And it's easy to check that the color pattern is what we want.
Can you go back to one slide? I'm slightly confused with the condition 1 and 2. So if IJK is in I star cube, then it also belongs to F cube, right?
Yeah, yes. You can put it in the first class or the second class.
The first class is exactly 1 over 4.
Ah, so for those cases,
Yeah,
you're
both
free to
are
choose
free.
whatever.
Yes. It's a little complicated, but it's easy to check that the key for 3 minus satisfies this, belong to this kind of graphs. And another one it's easy to check that the F5 star is a graph due to chain and shrink. We previously mentioned, and this graph F7 star. We put 3 new vertices x, y, z to this graph, and the link graph is also the 2 matching, and the link graph of new vertices are at disjoint. So by our theorem we deduce that this kind of graph is the uniform Turan density is also 1/4, and also so we skip the checking progress. Another corollary is about the wheel. The wheel is a graph on t vertices v0, v1, vt minus 1, and v0, vi plus 1 is an edge. So by our theorem, we can determine the uniform Turan density of the wheel. If t is even, the uniform Turan density is 1/4, and if t is odd, is 0. Because the blow up of hypergraph is a blow up of f have the same uniform Turan density with the original f. So we also have the double pyramid. The uniform Turan density is 1/4 if t is arc. So we know that the Turan density, the classical Turan density of all the double perimeter is at least 1/4. So it's interesting to determine the Turan density of all the double perimeter. So it is proposed to study this kind of questions. So about the strategy, we use the hypergraph regularity method. So we skipped the definition. We only give the reduced three graph. So I is the index set, and PIG, where R and G are all from the index set, and the PIG are the vertex class. For any triple IG key, the AIG key denotes the three-partite three graph with vertex class PIG, PG key, and PI key. So in fact, the reduced three graph are the size of I to two-partite three graph, and the vertex set are the union of vertex class PIG, and the edge set is the edge of three-partite three graph. We call it I-reduced three graph with the index I, vertex class PIG, and constituent AIG key. So given a reduced three graph, we see the reduced three graph is d-dense if for any IG key, the three-partite three graph, AIG key, the edge density is at least D. Okay. So how to embed a graph into the host hypergraph? So we have the embedding method. So given a three graph F and a reduced three graph, we see that the reduced three graph embed F if there are two mappings, phi and cosine. Phi is a mapping from the vertex set to the index set, and the phi from the shadow to the vertex set of the reduced graph. And if U and V belongs to the shadow, then the phi UV belongs to this vertex class. P phi U and phi V. And if UVW is an edge of F, then phi UV, phi VW, and phi UW belongs to this three-partite three graph. So by Reyer's lemma, if we want to show that the uniform Turan density is at most D, in fact, we should check this progress. If for any epsilon there exists n, where n is the index set, such that each D plus epsilon dense n-reduced three graph can embed F, then we call that the uniform Turan density is at most D. So if we want to show the uniform Turan density of some kind of F, then we check the embedding progress. So each D plus mu, D plus epsilon dense reduced three graph can embed F, then we call it, we succeed. So for us the key lemma is the following lemma. So for every epsilon, we find a bigger n, where n is the index set, such that each 1/4 plus epsilon dense reduced 3 graph. We can find a induced subgraph A prime on the set M1, M2, and in each part, in each color class, we have six special vertices, such that there are some kind of special edges between the vertices. And you can, if we can get this lemma, then we can embed our f into this hypergraph. Lemmas and structure lemmas. in the first part, we use the Ramsey theorem. I mean the hypergraph version to get some intersection lemmas. And the structure lemmas, we use some the Turan density and some previous result. So let's go to the key graph. Let's go to the key graph. In fact, it's Ryan Rodel and Matthias Schacht give a definition of a d mu g dense, where H is the d mu g dense if the edges touch all collection of key sets which spans a G uniform peak. If the density is at least either around D, then we call it a d mu G dense, called the H d mu G dense. Roughly speaking, when G is larger than the edge distribution of this hypergraph is more randomly. When G is equal to 0, then it is the classical one, and when G is 1, it is the uniform Turan density. It's easy to check that we have these inequalities. So pi f is the pi 0 is the classical Turan density, and pi 1 is the uniform Turan density, something like this. So Ryan Rodel and Matthias Schacht proposed to determine all these pi g f. So when G is equal to k minus 1, then the density is 0 for any f. So, and they give a characterization about the pi k minus 2 is 0. When the pi k minus 2f is 0, it means that f has a vanishing order of its vertices. What's the vanishing order? An order of v1, v2, vf is vanishing if the shadow of f can be partitioned to key disjoint set, and every edge is we I1, we I2, we I key. When satisfy this case, we remove one vertex when it belongs to exactly one case. So this is the case when key 3. So they generalized this characterization to the key version. So as we know, if the pi k minus 2 density is positive, then it should be equal or larger than this number. So 1 k 3 is exactly 1 over 27. It's a result of integral. So we give in fact we find some kind of graphs with this uniform Turan density. when G is K minus 2. So when K is 3 is the previous one. Okay. In fact, I give an example when K is 4. Okay. So this is a tight path, and it's a tight path. In fact, we give a sufficient condition to describe this property. The first one is that F have no vanishing order, and the second one is about for each pair Ig, the F can be partitioned into two spanning subgraphs F1 and F2, such that there is a vanishing order for both F1 and F2, and for two edges, if the Horman element is exactly K minus 2, then it is I type for F1 and G type for F2. So when K is 3, it's the same one as for the previous one. Okay, let us close the talk by the several problems. The first one is about the characterization of the 3 graph with uniform Turan density 1/4. The second one is there a dirt such that the uniform Turan density jumped from 1/27 to 1/27 plus dirt. The urgent thing is to solve this conjecture. I mean the uniform of Turan density of K for 3 is the conjecture is 1/2. And the third one, the third problem is about the uniform Turan density for clicks on T vertices where T is at least 4. And the last one is we want to know that whenever the classical Turan density is positive, the uniform Turan density is strictly lower than the classical one. Okay, thank you very much.
Thank you. There were no more pages, right? Right. Any questions? Please.
So what about the embeddings in uniform and dense graphs?
Sorry?
I mean, what about graphs?
Graphs. Oh, and for the graphs, because if we consider the quasi-random graph, if the density is positive, then we can find any subgraph. This is totally different from hard graph.
You showed the result in the beginning of Kamtsev-Letzer and Pakrovsky about the tide cycles. And you said that they settled it for divisibility case when it is not divisible by 3. Do you know why is it important and what happens when it is?
Oh, yeah, this one.
No.
It was about the density.
This one here.
That's 3 paratype, right?
Why do we need that case? Do you know? Or what is known about that case?
Then if L is divide 3, then it's 3 paratype, right? So
Ah, yeah, thanks.
Mm.
Okay.
Next question. So for the uniform Turan densities, the lower bounds, are they just coming from the like random graph, or is there like other sort of pseudo-random construction? Like how
Which one?
like any of the lower bound, like for the uniform densities, like the letter like the pi, the frequent dot dot. Like how so how like for any problem, like how does the lower bound comes from, like what sort of
Generally, they are from the random tournament or random coloring of a complete graph.
For the next for your theorem, you had this characterization in terms of coloring, right? So when you have such a coloring, then you have consequences. Could there be some kind of characterization, like what kind of hypergraphs satisfy, I mean, admit such a coloring, or what would be, what kind of graphs doesn't have that what kind of hypergraph doesn't have that coloring? I want to see some.
Yes. In fact, we can have the
Yeah, for instance, this one.
So in fact, we have another calculation. This means that when the f belongs to another kind of class, the uniform density should be larger than 1/4, but it's still using the coloring for the shadows.
I mean, it'd be nice to know, like, for instance, if hypergraph contains this configuration, then it doesn't have such a color.
It's not easy to give this even for the Turan, even for the Turan density 0.
All right. Any other questions? Yeah.